Welcome to qnawire.
Okay, in this problem we have a glycine molecule that diffuses 15 micrometers in water at a temperature of 20 degrees Celsius, and its concentration varies from 1 mole per cubic meter to half a mole per cubic meter. So this is a diffusion process. We assume the mass of the glycine molecule is 75 atomic units, 75 U, and we are asked for the time that it requires to diffuse in this way. And then we're asked to compare the resulting average speed of diffusion to the RMS thermal speed. So we're going to need a couple things here. The first thing is we need to look at example 18-9. Which gives us a diffusion time in terms of concentration. This diffusion time is the average concentration divided by the change in concentration multiplied by the distance squared, we'll call delta x, over this diffusion parameter d. That's a time. And of course, if we have a time scale and a length scale, then we can define a speed. We'll call this Vd for diffusion, just our delta x over delta t. Let's put a delta there. All right. And we can compare this to the RMS speed, thermal speed, which is simply root 3 kT over m, given by kinetic theory. So let's jump into it. We'll first find delta T. So our concentration varies from 1 to 1/2 moles per cubic meter. So the average is just 1/2, 1 plus 0.5. The difference is just 1 minus 0.5, of course, and the units are moles per cubic meter. Our delta x, 15 times 10 to the negative 6 meters, because it's micrometers. Got to square that as per the equation, the formula rather. And we divide that by the diffusion parameter, which in this case would be 95 times 10 to the negative 11 meters squared per second. Once we number crunch this, we end up with 0.3553 seconds, which is we can approximate to about 0.36 seconds. So we got our time scale. The average velocity for diffusion is thus going to be just delta x over delta t, which we found delta t. We know delta x. So 15 times 10 to the negative 6 meters divided by 0.36 seconds will give us about 4.2 times 10 to the negative 5 meters per second. Okay. Now we got to compare that to the RMS speed, the root mean square velocity for the molecules, just from random thermal motion, which is given by root 3 kT over m. K is the Boltzmann constant, which is 1.38 times 10 to the negative 23 joules per Kelvin. Multiply by kelvins, by its temperature. We're in water. We assume it's not 293. And we're given the molar mass. It's just 75 mass of a proton. We got it, 1.66 times 10 to the negative 27 kilogram. And once we number crunch this, we have 3.1 times 10 to the 2 meters per second. So you can see that the random thermal speed is way faster than the concentration, than the diffusion speed, rather, due to a change in concentration over distance. So to get a feel for how much larger it is, we can compare Vd to VRMS. So it's 4.2 times 10 to the negative 5 meters per second divided by 3.1 times 10 to the 2 meters per second. Let me double check something. Yeah, okay. I quoted the right answer. Just making sure. All right. So 1.4 times 10 to the negative 7 is this ratio. So you can see that the RMS speed is many, many orders of magnitude larger. In fact, about 7. And that's basically everything we're asked to look for. So just to recap, we started with this formula for the diffusion time. We divided the distance over this time to get an average diffusion velocity, and we compared it to the RMS velocity just using the expression from kinetic theory, root 3k T over m. And that's it.